Have you ever wondered what is really going on inside the AI that's suddenly everywhere? Today, we're going to peel back the layers on that black box. We'll start with the simplest ideas and build our way up, step by step, to something that looks a whole lot like an artificial brain. All right, let's dive in.
I mean, seriously, how does all this stuff actually work? It feels like magic, but it's not. The answer is something called a machine learning model. These are the engines that power modern AI, and they're all about learning from data to make smart predictions. Today, we're going to pop the hood and see how some of the most important ones actually tick.
So here's our roadmap for the journey. We're going to start with a really simple concept, just drawing a line. Then we'll see how a model can play a game of 20 questions. After that, we'll get into the wisdom of the crowd, combining hundreds of models. And we'll wrap it all up by putting the pieces together to build a basic artificial brain.
All right, first up, let's start with maybe the most intuitive idea in all of machine learning, finding a single, clean line to divide our data. This is the core idea behind a whole family of models, and they're called linear classifiers. So imagine you've got a bunch of data points. Let's say some are spam emails and some are not. The job of a binary classifier is dead simple. Draw a boundary that cleanly separates the two groups. Anything that lands on one side, we'll call it spam. Anything on the other, not spam. Simple, right?
But not all lines are created equal. I mean, look at the line on the left. Sure, it technically works, it separates the dots, but it's cutting it really close, isn't it? It feels fragile. The slightest new piece of data could flip it to the wrong side. Now, look at the line on the right. That feels so much better. It gives both groups plenty of breathing room. It's a much more confident and robust choice.
Well, that breathing room actually has a technical name. It's called the geometric margin. And this is the entire secret behind a super powerful model called a support vector machine, or SVM. Its one and only goal is to find the single best line that makes that margin, that empty space, as wide as humanly possible. It's not just about getting the answer right, it's about being as confident as possible in that answer.
Okay, so drawing one line is great, but what if your data is way more complicated than that? What if a single line just isn't going to cut it? Well, let's switch gears and look at a totally different approach, one that works a lot like a game of 20 questions. Let's talk about decision trees. The logic here is completely different. Instead of trying to find one big perfect rule, a decision tree just asks a series of really simple small questions. Each yes or no answer splits the data into smaller and smaller piles. It's basically a strategy of divide and conquer, and it's incredibly effective.
Let's make this real. Say we want to predict if you can go skiing based on the month and your latitude on the globe. Now, if you look at the data, you can clearly see two big clusters, right? There's a winter season up in the northern hemisphere and another one down in the southern hemisphere's winter. So how would a decision tree figure this out?
Well, it might start with a really broad question, like, is the latitude greater than 30 degrees north? Boom! That one question just split the world in half. Then, for just that top half, it asks another question. Okay, is the month before April? And just like that, with two simple questions, it's already carved out the prime ski season for North America and Europe. It just keeps asking these simple questions, chopping up the data into these neat little predictable boxes.
So a single decision tree is pretty clever, but what if we used hundreds of them all at once? That's the powerful idea behind our next stop, ensemble methods.
Here's the catch with a single decision tree, though. They can be a little unstable. If you change the data just a tiny bit, you might get a completely different tree. This is what we call high variance. It's like a student who just memorizes the answers for one specific test. The tree can overfit, meaning it learns the random noise in the data instead of the real underlying pattern.
So what's the fix? Well, it's teamwork, pure and simple. Instead of trusting one single potentially flawed expert, ensemble learning is like asking a whole committee of them for their opinion. By averaging out all their predictions, you get a final answer that's way more stable and accurate than any single one could be on its own.
And the random forest is probably the most famous example of this. This is where it gets really cool. We start by building hundreds of different decision trees. But, and here's the secret sauce, we inject randomness into the process. Each tree only gets to see a random portion of the data. And at every step, when a tree has to make a split, it's only allowed to consider a random handful of the possible questions it could ask. This forces each tree to learn a slightly different part of the problem. Then, for the final prediction, they all just vote. It's this beautiful process of forced diversity that averages out all the individual errors and gives you an incredibly robust model.
Wow, okay. We've gone from lines to a whole forest of trees. For our final stop, we're tackling the big one,
the model that powers almost all of modern AI, the neural network. Now, I know it can seem like this totally mysterious black box, but you're about to see that it's actually built from ideas we've already talked about.
To understand a neural network, you have to forget all the complexity for a moment. Because every single bit of it, boils down to one simple building block, the artificial neuron.
So what does this one little neuron actually do? Well, you might be surprised to hear this, but a single neuron, it's basically the same idea as the linear models we started with. It just takes a bunch of inputs, multiplies them by some weights, adds them up, and spits out a signal. That's it.
The real magic, of course, isn't in one neuron. It's how we connect them. We take a bunch of these neurons and line them up side by side to form a layer. Then, and this is the key, we stack these layers on top of each other. The output from the first layer of neurons becomes the input for the second layer, and the output of the second layer becomes the input for the third, and so on. That is the core idea behind deep learning.
And this is why having that depth is so incredibly powerful. The first layer might learn to recognize really simple things, like diagonal lines or bright spots in an image. The next layer takes those simple patterns and learns to combine them into more complex shapes, like an eye or a nose. And the layer after that learns to take the eyes and noses and recognize a complete face. Each layer builds on the one before it, learning more and more abstract concepts as you go deeper.
So there you have it. We've gone from drawing a simple line to playing a game of questions to harnessing the wisdom of a crowd, all the way to a model that's literally inspired by the human brain. We've seen how these powerful tools are built not from magic, but from stacking simple ideas on top of each other. These are the fundamental building blocks of the AI that is reshaping our world. And it leaves you with one pretty exciting question. What will we build with them next?